Hey everybody, and welcome to Chapter 2. As you can see, this time around I have my handy little stylus so that I can do really cool things like this. That's fun, right? I can draw on the slides now. Anyways, thank you so much for joining me on this journey into Chapter number 2 of Psych 308, Statistics for Psychologists. What this chapter is going to be about is mostly kind of like how to represent data. So like how to visualize it. So we're going to be talking a lot about graphs and what graphs are appropriate for what kinds of data. You may remember in Chapter 1 we talked about different kinds of scales of measurement. And I mentioned that, depending on the kinds of scales of measurement you have, you might run certain tests. And this is just kind of an extension of that. We haven't really talked about what tests we're going to be running, but we're at least going to be talking about how to visualize our data. And I think this is important because you see this a lot online and in newspapers and things like that, where data are represented poorly, so that they are at best misleading and at worst dishonest. So we're going to go through these. There's not actually going to be very much calculation at all in this chapter, and that's just because a lot of it's just talking about data visualization. There is one section where we will be breaking out our pen and paper, but nothing too serious. All right, so let's get into it. We're going to be doing the more serious calculations starting, I think, in Chapter 3 when we start talking about central tendency. But we'll get to that when we do. Alright, so the most basic, straightforward way of representing data is with a table. And I'm going to go over this even though I know it's really obvious, but usually in a table, what you're going to find in most cases is that the columns tell you something about a variable or that the rows tell you something about a variable. So here, what we're looking at is Springfield Tech versus Holyoke. So we're looking at the different kinds of students who are full-time, and in Springfield Tech we can find that that number is 9,200 out of a total 22,496. I know that you know how to read a table, you got to college, but I just wanted to kind of point out that this is, it is kind of a very boring way of expressing data, but it is a useful way. So when would you want to use this? You'd probably want to use this if you were using a nominal scale where you're using something like splitting people into full-time or part-time. Because that's, if we were to kind of break it out into how many credits are you taking, 18 versus 15 versus 12, so on, each semester, that would be a little bit different, but we're looking at nominal scale. Why is it nominal scale? Because we have full-time, we have part-time. That doesn't really tell us much, right? Like full-time tells us that they're probably taking somewhere between 12 hours and 21 hours, and they're part-time at somewhere between maybe 1 hour and 11 hours, right? So it doesn't really tell us all that much. But we can still show the number counts, the frequency counts, and we can put that into a percentage. We'll talk more about how to turn it into percentages later. But this way, it's nice, it's very, very specific, but probably not really all that helpful if you're trying to catch someone's attention, right? You might use something like a pie chart to do that, which is what we see here. So if you have nominal data and you want to express it in a way that is graphically pleasing, a pie chart is the way to go. And I know a lot of you know about pie charts, but basically inside this circle you're going to get 100% of all of your data, and then you're going to split it up into different slices based on the proportion of that data. So in the previous graph, we were looking at in this case, 51% of students were part-time and 40.9% were full-time, and that's just expressed with a slightly more than half, right? So this would probably be 9.1%, so slightly more than half of the pie is dedicated to the part-time folks. And if we look at Holyoke, we can see there's a huge difference. So the reason why I was saying that, that this is an important thing to visualize is because if you're just looking at that table, you might not realize as easily or as quickly or as effectively that the big difference here is that Holyoke has many more part-time students than Springfield. And you can kind of see that discrepancy there. So this pie chart is a good way of doing that whenever you have categories of data for that. We're not going to really use pie charts all that much in our class this semester, and the reason for that is just because with pie charts you're usually working with nominal data, which is really hard to analyze, or not the most detailed data set. So most of the stuff we're going to be doing is not really going to fit into these qualitative examples. Here's a much more complicated version of a pie chart. So here again, if we were to add up all the percentages here, it's going to give us 100%. And we can kind of see, where psychologists work out of 100%. So 33% of people work in higher education, 15% work in hospitals, 21% work in business or government, 6% have independent practice, so on. You get the idea. Looks like K through 12, some of them are going to be special ed teachers maybe, or I've seen psychology majors who go on to be psychology teachers in high school. So that is how that's represented. Here we have the different areas of specialization. I thought this was really kind of interesting because more than half of people who major in psychology are interested in this counseling piece. And we're going to see some school, some developmental psych. My folks over here, the cognitive psychs, where are you guys at? Why is there only 3 of us, or 3% of us? All right, so that just gives you an idea of the pie chart. Next up, we have the bar graph. The bar graph is also going to be used for nominal data whenever you're talking about using categories. So again, you can kind of see that we're using the same data with Springfield and with Holyoke, and we're looking at full-time versus part-time. And again, we can kind of see the different proportions here, but really this is not, I would say this is not the best. I mean, depending on what your question is, this is probably not going to be the best graph that you want for the data set that we just had. And the reason why is because I would be interested in looking at, what is the percentage of people who are full-time versus part-time. Using a bar graph is going to be much better at looking at proportions or frequencies, mostly frequencies. And the reason why I say that is because here with Springfield, there's just many more students, right? And so so it's really hard to kind of compare the proportions or the ratio of full-time to part-time whenever you have so many more students at Springfield Technical than at Holyoke. So here, this does show us the imbalance of part-time versus full-time, but it also shows us that Springfield Tech has many more students than Holyoke. That's something that these graphs right here don't really communicate, right? These pie charts don't communicate the total number of people there, which is, that might be something that you're trying to get across to your audience. If you don't feel like that's important, then you can go with the pie chart. But again, you making that decision, you have to make sure that you're not trying to mislead people with your data that way. So here's another example, and I think this one does maybe a better job of showing why nominal you can't use other things like line graphs or scatter plots for. So if I were to poll our class and ask, what kind of pet do you own? I'm going to get some people who say dog, some people who say cat, some people who say fish. Maybe we got a few rabbit fans out there, hamsters. I don't know where the bird folks are. But here we see that there are many more. The highest group is going to be the cat. The lowest group is going to be the rabbit, right? But we can't say, for this x-axis, because this is going to come up soon, that this x-axis down here, that this does not have a measurement scale to it. It is not like rabbit increases to become dog, and dog increases to become cat, and cat increases to become goldfish. It doesn't move on the scale that way. Instead, these are just categories that are kind of arbitrarily put here. If we mix these up and put them in alphabetical order, it would not change anything, right? It would not be dishonest for us to do that because the scale here is nominal. And so I just like this picture. This is from How I Met Your Mother, where Marshall is explaining that this is a pie chart describing his favorite bars and a bar graph describing his favorite pies. Kind of fun to talk about, but again, just be careful because sometimes drunk people like this guy right here might try to mislead you with the kinds of graphs that they are being creative with. Instead, we're going to be spending most of our time this semester looking at quantitative data. So most of the time we're going to be looking at quantitative data because it's going to give you a lot of flexibility. There's a lot of ways of showing data with quantitative means. So examples of things that we might try to show using these quantitative graphs is behavioral changes over time. So if you want to show, like, over the course of time, how does someone's behavior change? Do their treatment outcomes get worse or do they get better? Do they, if we're looking at socialization rates, like how many times do people have conversations with others over the course of a week? If you're working with somebody who's really introverted, you might plot that out to see, like, oh, like over the course of the week, they become less social, So any kind of change over time, you're going to want to use a quantitative graph. If you're looking at how treatment affects behavior, so if you're looking at like a before and after type of thing, that is also going to be with a quantitative data set. If you're looking at how variables interact with one another to cause change, or even if you're looking at how certain qualitative variables affect quantitative variables, those are all going to be questions that you can graph and visualize using quantitative scales. So the thing to consider here, and we're going to go through a couple of examples of this, is are you using the appropriate figure for your data scale? And what are you trying to emphasize with your figure? Those are two important questions to think about whenever you're choosing the scale for your data. So, stem and leaf plots. Honestly, this is maybe my least favorite of the ones that we're going to be talking about today. And the reason why is because I never see this in the wild. The only time I ever really see them, pretty much, is in stats classes and in stats books. I remember there was one research paper that I saw where somebody did use this, and I was shocked because I had never seen it anywhere else except for in stats textbooks. But because they are in every single stats textbook, I'm going to teach it to you just in case it ever comes up. But basically, a stem and leaf plot, you got your stem, you got your leaf. The stem is going to be whatever the first number is in your numbers. So, for example, we have numbers that go from 15, 16, 21, all the way to 41. If we want to graph out to get an idea of what our data look like, we can start grouping up. Okay, these right here, 15 and 16, they both start with the number 1. So for the stem of 1, we have a 5 and we have a 6. And that lets us know that in this data set that we have a 15 and we have a 16. Now, we can look at the 20s and we can see that these go up to these right here. So for the stem of 2, right here, we have a 1, a 3, a 3, a 6, and another 6. So if I were to ask you, like how would you plot out 32, you go for the stem of the 3, which represents the 30s, and then you put in the 2 for 32. So again, is not really one that you're going to be using all that much, probably out in the real world, but it's an easy way to organize your data, and it's easy to read. It doesn't take a lot of time to read, so if you want your reader to have the specific numbers on hand, the stem and leaf plot might be the way to go. More commonly, you're going to see something called histograms. And histograms I like because they give you a good picture of the shape of your data. Okay, so I'm not going to geek out a little bit. I could talk about the shape of data a lot because we're going to be talking about the shape of data a lot this semester because, well, the shape of the data can tell you a lot of different things. It can tell you about what data is most common, what data is least common. It can tell you if there's any kind of skewness in your data, what kind of variability you have in your data. These are things that we're going to be talking about later in the semester, so it's okay if you don't know about skewness and you don't know about variability. We're going to get to it. But we're going to see a lot of histograms this semester. And a histogram basically works like this. And I know you may be thinking, hey, this looks like a bar chart. How is this different than a bar chart? The difference is going to be what the x-axis represents. So you may remember I was pointing out the x-axis earlier in the bar chart to show that it didn't really make sense, But here, for height, the x-axis does follow a pattern, right? It goes from lower values to higher values. That's because we are not working with nominal data anymore. Now we're working with at least ordinal data. And usually if you're using a histogram, you're going to be using either interval or ratio. But you can see that here what we're showing is that for people that have height between 55 inches and 60 inches, we only have one of those people. For people that are between 60 inches and 65 inches, we have 7 of those people. How many people do we have between 65 and 70? You guessed it, we have 5 people. So this is a nice, easy way to show buckets, or what they call bins, of people. This isn't something you would be tested on, but these little intervals that we have here, those are just called bins. Basically the x-axis is going to group up these bins so that we can say, like, all right, we have one person who's below this threshold, we got one person who's above 75 inches, and so on. So it's a nice way to display the distribution of your data. Now, frequency polygons are going to be a little bit different. The difference with frequency polygons is basically it's just not in a bar like that. You don't have those kinds of polygons. Sorry, I thought I could erase. There we go. I'm erasing it. Basically, a frequency polygon is going to give you the shape of the data. It looks a little bit like a mountain in this case, but it's the same idea, where you're going to be grouping things based on these little buckets or these little bins right here. Line graphs are, again, a little bit different. Line graphs, the difference here is that the x-axis has to be an interval or ratio. Previously, when we were talking about frequency polygons or histograms, those could be ordinal if you needed them to be. Not so with line graphs. So with line graphs, you have to pay attention to the x-axis here, that these do not have buckets, right? That these are basically looking at, okay, here's for 5 p.m., here's for 6 p.m., here's for 7 p.m. And so this x-axis right here is going to be looking at the time of day, and we can kind of see, over the time of day, the number of yawns that take place. So we got a lot of yawns right around whenever work gets over. We have very few yawns, when we're watching, I don't know, whatever your favorite TV show is that comes on late at night, and then we have more as the night wears on. So in this case, what we're looking at is the relationship with the time of day and how much someone yawns. All right. Line graphs can be really complicated, but you can also use them to compare across other kinds of variables. So this is looking at brain temperature and yawning. I don't remember where I got this data, to be honest with you. I think I was looking for examples of like line graphs, and I came across this one, and I was like, wow, this is really, really fascinating. Who would have thought that brain temperature varies based on the yawns that you make? And so what we're looking at here are 3 different conditions: one where participants yawned, one where they yawned and stretched, and one where they just stretched. And so here you can see that this is minutes from yawn, so this is the 0 hour, meaning that this is exactly where people yawn. And you can see that whenever people yawn, that their brain heats up a little bit. But if they yawn and stretch, that it doesn't heat up as quickly or as dramatically. So you can compare these multiple lines so that you can draw comparisons across conditions, something that we will be doing a lot this semester, actually. So this graph is showing the average across these conditions, which is something that you can do if you're working with line graphs. You can use them to represent a group if you like. All right, and I should emphasize that the y-axis here does not have to be measuring frequency like the histogram or the frequency polygons do. All right, I'm going to cut the video here, and then we're going to pick up for box plots because that does require a little bit of calculation, but I will catch up with you there. See you soon.